Example 3 of the disk method. This is a solid of revolution. So in this example, we're given this equation, y equals x cubed minus x plus 1. We're told that the region we're desiring is going to be bounded by this function, x equals 1, and we want to go about the x-axis. So my first step is to actually graph this and see what's going on. As I put it in my graphing calculator, I did zoom in, so I used a window that went from -2 to 5 for the x's, from -1 to 5 for the y, so I could get an idea of what was going on here. I see that my function is a cubic, and that I want to put a boundary of this of x equal 1, which would be right here. And so, as a crude graph, I simply mirror what I'm looking at. I've got this function that's running up like this, comes down, goes back up, and then I've got this, I'm looking at my calculator, this x equals 1 here, which is cutting that off right there. It tells me that this is the region that I want to revolve about my x-axis. In order to do this, I'm simply going to say the volume will equal. Now, I probably need to figure out what this value is right here, because I know where I'm going to finish at. It's going to finish at 1, but I don't know where this value here is. So on my calculator, I can go second trace and find that 0, find where it's crossing the x-axis. And so I just scooch this over. I do boom. Beneath the x-axis, above the x-axis, I guess, and I'm getting a value of -1.3247. So I'm going to do x equals -1.3247. As I've said a number of times, when you're doing your integrals, your final answer should always be rounded to the third decimal place. You should keep 4, even 5 decimals on your integral, because your calculator is going to do all the work. And then, as we said a moment ago, I'm going to finish this at x equals 1. Formula will be pi. My radius has to be from my axis of revolution up. So one direction, one dimensional would be this. It's just the function. So it would be that entire function, x cubed minus x plus 1 squared, and then I throw a dx on the end. That's my pi r squared h. That's a disk. Infinite sum of disks that start at -1.3247 and at 1. Now I'll put that in my calculator. Notice here was the original graph, but that's not what I'm integrating. So I go back to the y equal. I'm going to insert a pi, a parenthesis around that function, because that function has to be squared. Now I can regraph this. This is representing volume now. It's no longer the area. And so I'll still do the integration option, which is option 7 on the TI-84. I'll tell it where to start, where to end. So I want to start at a -1.3247. My upper limit would be at 1. And as it shades this in, it's going to report a value. I can't stress enough, the value that it's reporting is the volume of this region as it's been rotated around the x-axis. So I'm getting a volume that is equal to, put my calculator, I don't even look at it. It was 7.168. And you see how I rounded 3 decimal places here. And of course we'll say units cubed. There's your third example of how to do the disk method. This is part of our Solids of Revolution series. So disk method, I took the function, figure out what that radius was, squared it, applied the formula, pi r squared h, and your h is just your dx, threw it in the calculator, and came up with this answer. Example 3.